All right, so this is 15.6. This week we're going to be doing 15.6, 15.7, 15.8, and 16.1. The good news is that two of those sections will be relatively simple in terms of computations, in terms of concepts. And that's great because two of those sections are probably some of the most important sections we'll be doing in the class. That would be 15.7 and 15.8. Okay, so that means this section right here is one of the more simple ones, and that's linear approximation. All right, so the idea behind linear approximation is exactly the same as in one variable calculus, where you had a function, the values of the function are too hard to compute, and so you draw the tangent, or at least visually, you draw the tangent line, and as long as you know information about the function at one particular point, for example, its value and its derivative, then at other points nearby, right, instead of calculating this value, which is what you want, that's f of whatever that x value is, you calculate the value up there, which is super simple because it's just from the equation of a line. All right. We've talked about this quite a bit in previous sections, but in two variable calculus, you have the same idea, except your graph would look curved, something like that perhaps. And instead of, if this is the one point, so everything works actually in analogy exactly the same as in one variable calculus. So again, you're going to need one point where you know everything you need to know about the function, which is its values and its partial derivatives. And if you do, then you can draw the tangent plane here, again, in terms of visually. And if you need to figure out values of the function nearby, you can go up, and instead of calculating the exact value, which is the value on the graph, you keep going until you hit the tangent plane, and that's your approximation. All right, so I guess I should label, this is my approximation, this is the actual value. Right? And it's the same idea on this right-hand side here. That's my actual value. That's my approximation. And for all of these, the approximations are ridiculously easy to compute because, well, in the first case, it's just a line. In the second case, it's just a plane. Okay. For multivariable calculus, we've talked about this quite a bit as well. You need your function to be differentiable. And that essentially, we've said, means that linear approximation works. So that means that when you do this approximation, you know there's a certain amount of accuracy involved. And you can analyze that. We're not going to worry about it. Of course, in real life, anytime you do an approximation, you actually should be saying, my estimate is whatever, 3.7. plus or minus 0.2 or something like that, all right? We're not going to do that kind of analysis, but if your function is differentiable, if it's actually second differentiable, then you can actually do a very, very careful analysis. Maybe you did something like that in one variable calculus. Usually you don't, but it definitely can be done. Well, actually, you kind of did it when you did Taylor series, right? Because the first, the Taylor series with just the x to the 1 power is linear approximation. And then you had the remainder terms and you did a whole bunch of analysis with that probably in second class in calculus. Okay, so let me, again, I've done this before. If you think you understood it fine the last time, perfectly fine. You can skip over this perhaps, but maybe it's good to see it again. I'm going to derive the formula for linear approximation for multivariable calculus. It's good to see because it means if you can't remember the formula, you can figure it out relatively quickly, actually very, very quickly. And it's also good to see because it uses a lot of the stuff we learned from the earlier parts of the class. Okay, so what exactly is, how do we do the tangent, the linear approximation? or tangent plane approximation, we figure out the equation of the plane, right? So what's the equation of the plane? Well, let me draw the same picture. That's gotten a little messy there. X, Y, Z. This is the point where we know everything we need to know about the function. Let me draw the graph up here. Let me draw the tangent plane right there. That's the plane that we're whose equation we're looking for. Right, here's our, this is looking a little messy already. Here's our point of, here's our point of interest. There's the value of interest. Let's say our point of interest is A comma B. And again, the entire point here is we can compute f at A comma B. We can compute partial derivative of x, partial derivative of f, partial derivatives of f at A comma B. All right. For all these linear approximations, right, all these versions of linear approximation, there needs to be a point where you understand the function. Okay. So what exactly is the equation of this plane? Well, we can look in the x direction, right? And then if we go up here, this is going to hit the graph, and it's going to be a curve, right? Maybe something that looks like that, for example. Let me exaggerate it a little bit, just to make it more, visual. So we go up, we get a curve. Let me exaggerate it like that. Okay. This curve, we can talk about its tangent line, right? We could parameterize this curve. That would be super easy because you just you're only moving in the x direction, right? So it would be a nice parameterization would be t comma b, right? Or a, let's say a plus t comma b, so that t equals 0 corresponds to a. So if you do this parameterization, sorry, you have a one variable. You can do the composition function with f, which is your main function, your two variable function here, and that gives you a vector valued function, which allows you to calculate a tangent direction. All right. So if you get this tangent direction, then you've got one piece of the puzzle for calculating tangent plane, because this blue arrow here, that lives on the plane. All right. If the tangent plane means anything at all, in other words, if your function is differentiable, then that blue arrow lives on the plane. All right. Okay. Why do we care about that? Well, we're going to do exactly the same thing as y. We're going to get another direction like that lives on the plane. And then in order to get the equation of the plane, well, if you have two arrows or two vectors that live on a plane, you take their cross product and you've got something which is normal. All right. Let me kind of make this look a little bit more normal. Right? Then you've got something that's normal. And remember the equation of a plane, what do you need? You need a normal direction and you need a point. Right? The point, we're all set. Because we're looking at a comma b down here, that means this point upstairs is a comma b comma f of a comma b. Right? And again, theoretically, the way we use this, we know a, we know b, we know f of a comma b. Those are all computable quantities. All right, so let's compute the or try to figure out the equation of that that arrow right there. All right. So I think a good way to do this, 3D is often hard to visualize. So what we're going to do is we're going to make a cut like this. We're going to cut this whole picture with a plane that passes through a comma b, and that's parallel to the xz plane. All right. And so what's going to happen is this blue arrow is going to become. Let me draw the x and z here. All right. So this is happening at a comma b, plane parallel to the xz plane. That blue arrow is going to look something perhaps like, if I just kind of follow that picture, it's going to perhaps look something like that. The graph of my function is going to look something like that, right? And down here, my point of interest is going to be at x equals a. And again, y is fixed at b. Okay, so this is the this is my function, and if I were to write it out, it would be f of x comma b, right? Because again, we're fixing our y coordinate at b. Okay, so that's a one variable calculus function, and so essentially we can calculate this the kind of direction of that arrow using the ideas from one variable calculus. And the idea is, well, we know that the slope of this arrow is what's going on? The slope of this arrow is df dx, right? Because it's the tangent direction, right? And that's literally what we learned, what df dx was from one variable calculus. All right. Of course, we're looking in the x comma z plane, but no real difference in terms of what's going on here. Okay. So if the slope of that guy is df dx, what exactly is this in terms of a vector? How do we write it in terms of a vector? Well, the slope is df dx means, right, if you have a line with slope 3, what that means is, or one way to think of it is, if you're on that line and you move one step to the right, you need to move 3 steps up to stay on the line, right? That's what slope 3 means. Okay, so if your slope is df dx, that means if you move 1 step to the right, you have to move df dx steps, either up or down, right, depending on whether df dx is positive or negative, in order to stay on that line. Okay, so here we're right there, right? We need to, if we move 1 step this way, then we need to move 1 step that, we need to move df dx steps that way. Okay, right? And in this particular picture, df dx happens to be negative. All right. Okay, so what does that mean this vector is? Well, a vector that's 1 step to the right and then df dx steps down. Again, down is in the z direction, is going to be I plus 0j, right? Again, y is fixed, so of course 0j. And then plus df dx. K. All right. So that's the vector that that we're looking for, right? So that's one vector on our tangent plane. So this is on tangent plane. All right. So I plus df dx k. Okay. So like we said, all we need is another vector, and we just do the exact same thing, except in terms of the y and z directions. We cut a plane at AB parallel to the YZ plane. And then we get, again, a picture that looks exactly like this picture here that we drew, except, again, in terms of y and z. And, of course, we're going to get something like 0I plus, and then this time it's going to be 1 step in the y direction, means we have to make df dy steps in the z direction, right? So it's going to be plus 1j plus df dy steps in the z direction. Okay, and that keeps us on, if we do this kind of, steps thing, it keeps us on our line. Okay, all right, which means that these two represent the directions in our tangent plane, 2 directions in our tangent plane. Okay, so the normal is going to be the cross product. So ijk, let's do it this way. The first one is 1, 0, df dx. Second one is 0, 1, df dy. And then if we actually calculate this, we're going to get minus df dx times I, minus df dy times j, and then plus 1 times k. Let me just write plus k. All right. Okay. Once we've got the normal on the plane, so that would be the equation of this thing that we just found is the equation of this normal right there. Okay. All right. So we've got a normal, we've got a point, oops, we've got a point, which we said was a, b, f of a comma b, right? And I guess I should emphasize, all of these df dx, df dy's, right, where are they happening? They're happening at a comma b, right? Evaluated at a comma b, evaluated at a comma b, right? If we look up at our original computation here, right, we're calculating the equation of this tangent line right there at a, right? And then, of course, we're taking this vertical slice at y equals b. So everything is happening at a comma b. Okay, so in particular, if we want to be really careful about this, this would be happening, oops, this would be happening at a comma b, this would be happening at a comma b, that's at a comma b, that's at a comma b, right? And I want to emphasize that because, again, if you actually want to do linear approximation, you want to do calculations with this, you actually need to know the values of f of ab, right? You need to actually be able to calculate that, like that's equal to 4 or something like that. You need to know df dx at a comma b to be, something like 7, and df dy at a comma b to be 10, right? You don't need any other values, but you do need those. Okay, in any case, that means my plane is going to have equation x minus a, right, times the first component of the normal, df dx, at a comma b. I'll fill those in later. Minus df dy at a comma b, y minus b, right? Just using the a, b, and then last one is going to be plus 1, because the coefficient of the k is 1, times f of ab. Sorry. Guess I got a little ahead of myself there. Plus 1 times z minus f of ab is equal to 0. All right. Okay, we're interested in linear approximation, where essentially we want the height z, so we solve for z, right? Because the height of this plane at whatever inputs, x comma y inputs, is going to represent our approximation. So we need to solve for z. And if we do that, we throw everything to the other side except the z's. We're going to end up with z equals df dx, x minus a, plus df dy, y minus b, and then plus f of ab. All right, and then now let me fill in all the at ab. Again, just to emphasize, all of this is happening at our point of interest. And so if we do know those values, we're all set. Okay, so notice that, remember in one variable calculus, so one variable, your linear approximation formula was f prime at a, x minus a, plus f of a is equal to, let me call it y, right? If we calculated the line, the equation of that line, if you compare the two equations, they look almost exactly the same in spirit, right? You have the derivative, and now you have the derivatives, because you've got two different directions now. You have kind of the linear portions, right? The x minus a and the y minus b. And then you have the actual function value as the last term. Okay, so if you're comfortable with one variable calculus linear approximation, this is a very small step forward. Okay, so the way we use this is f of x comma y is often too hard to compute, and so instead we say this is roughly df dx x minus a plus df dy y minus b plus f of ab. All right, and again, this is at ab, this is at ab. Okay, and it's always good to emphasize, right? How do you actually compute this right-hand side? Well, like we said, you're supposed to know f of ab. You're supposed to know df dy. You're supposed to know df dx at ab. So if you do know those things, then the only thing you have to do to compute this right-hand side is multiplication and addition. All right? So anybody can do this. A first grader could do this. So a first grader could estimate values of complicated functions as long as you gave them this right-hand side as the estimate. Okay, so that's actually the power of linear approximation. Okay, so for example, right, estimate f of, let's say, 1.2 comma, let me fix that, comma pi over 4 plus 0.1, where f of x comma y is equal to, let's say, natural log of x times sine of x, sine of y, sorry. Okay. All right, so the idea here is we know everything we need to know about our function at 1 comma pi over 4. We know f of 1 comma pi over 4. We know f sub x at 1 comma pi over 4. We know f sub y at 1 comma pi over 4. And if we know these three guys, then we can estimate f at any value, right? And of course, we'll get good estimates if we're nearby. Okay, so let's actually calculate these. F of 1 comma pi over 4 is going to be 0, right? Because natural log of 1 is 0. Let's calculate the partials. F sub x is equal to sine y over x. And so f sub x at 1 comma pi over 4 is going to be equal to root 2 over 2. F sub y is equal to, well, this one is actually going to turn out to be 0, but let's do it anyways. X, natural log of x times cosine y, right? So f sub y at 1 comma pi over 4 is going to be equal to 0. All right, and it's perfectly legal to have a term be 0. It just means that in a first order manner, or when you're thinking of first order change, your function is not changing in the y direction. Okay, so this was root 2 over 2, and this second one was 0. All right, and so f of anything, right, let me write down the general formula, is approximately, so here we can just quote the formula, right, df dx at our point of interest. So that's going to be root 2 over 2 at our point of interest. So that was, f sub x at our point of interest, and then x minus 1, right? Because again, our what we would have called the base point in single variable calculus is 1 comma pi over 4, all right? Plus 0 times y minus pi over 4, and then plus f of 1 comma pi over 4, which is 0, okay? And so f of x comma y is approximately root 2 over 2 times x minus 1, which again is perfectly legal, right? It can be simple. It could even be just 0, right? That would mean that at your base point, your tangent plane is actually flat, which is, again, perfectly legal. If you did the one variable calculus linear approximation for, let's say, cosine of x at x equals 0, you would get the same idea, okay? All right, so, and again, we could technically apply this approximation anywhere we like, but generally we like to apply it only nearby our base point, because otherwise things get less and less accurate as we move away. Okay, so this is going to be approximately simply root 2 over 2 times 1.2 minus 1, right? And again, you see the power in that once we've gotten this formula over here, you don't need to know any math anymore. You don't need to know any calculus anymore. All you need to do is be able to add and multiply, right? So this is root 2 over 2 times 0.2, right? And so that's root 2 over 10. Okay. All right, and again, in real life, you would need to analyze this a little bit more, and you would like to say your answer is this, and then plus or minus a certain threshold, right? Otherwise, if you don't know how accurate your approximation or how inaccurate it might be, then you can't really use it. Okay. So that's linear approximation. Let me write it again. F of x comma y is approximately, let me use the f sub x notation now. B x minus a plus f sub y, ab, y minus b plus f of ab, right? So that's our formula for linear approximation. And again, if you can't remember it on an exam or whatever, very quickly you can derive it, right? From the basic idea. All you have to remember is you need to kind of cut in the x direction, cut in the y direction, and then you can get the equation of the plane through the cross product. Through the cross product giving you the normal. All right, so one application was kind of the one we just did above, relatively straightforward. You can do this with different functions. You want to find base points that are appropriate, right? That are perhaps nearby where you want to estimate, and so on. The homework problems in this section are going to be mostly that, right? But there's one more kind of homework problem in this section, and that's differentials. And you almost certainly talked about this in the corresponding section from one variable calculus. And the idea here is that, let me put these in quotes because I hate this word, at least the way we use it in calculus. So the idea is sometimes you don't actually want to estimate the value of the function, of a function. You only want to know how much things change, right? And so if you think about this, approximation here, if I throw this f of ab to the left-hand side, right, f of x comma y minus f of ab is approximately f sub x at ab, x minus a plus f sub y at ab, y minus b. If you think about this left-hand side, this is how much your z coordinate, or the value of your function changes as you move from the point a comma b as your input, right, to the point x comma y as your input. Okay, so we can call that, for example, delta z, right? How much the z coordinate changed, or delta f. But let's kind of use delta z. Maybe it's more visual. If you think about this term right there, x minus a, that's how much your x coordinate changes, right, as you move from a comma b to x comma y, right? So maybe a picture in your head should be something like this, where our base point is a comma b, right? We're thinking about what's happening at x comma y, where we understand the function less, right, than at a comma b. So this x minus a represents that distance there, right? And it's the change in x, right? The difference between the x values. So this we can call delta x. And then finally, this guy right there is the change in the y, right, as you move from a comma b to x comma y. And so that we can call delta y. All right. And so ultimately, you can write down a kind of formula that says delta z, or delta f, depending on what you want to call it, is roughly f sub x ab delta x plus f sub y ab delta y. All right. Okay, so nothing really happened, right? We just wrote down our original linear approximation formula up here, and we just manipulated a little bit to get a different, in a way, just a different point of view, right? This point of view is about change. How much does f change, or the output change, or the z coordinate change, or the height change, compared to how much the x changes and how much the y changes? All right. So sometimes we're actually not really interested in the actual value of the function, but rather just how much things change. Okay. So this is the formula for change. Again, I'm going to stick in this delta f because that's often used as well. This allows us to kind of estimate the change. Right? And again, estimate, because we always have to remember this is squiggly lines here. This is not equal. All right. So there's always some amount of error that we're making here. Okay, but Regardless, the idea is still the same. This quantity right there, we know, right? This quantity we know, so it's just a number, right? So in practice, we might have something like delta f or delta z is equal to 3 delta x plus 10 delta y, right? And so that tells me that if I change x by a certain amount and I change y by a certain amount, how much, oops, I should, again, use squiggly lines as I said. That tells me how much the output of your function should change, roughly. Okay, and this gives me some nice information, right? Just looking at this, I can say that, well, changes in y cause, are more, in a way, are more important in terms of how my function changes compared to change in x, because of the 10 here versus the smaller number 3. Okay, that's the idea behind this. All right, before we do an example, let me mention this deal about differentials. So if you look in our book and the homework and stuff, and most books, almost every book is going to use the notation. So I use deltas. Of course, this is often seen as df is approximately f sub x a comma b dx plus f sub y a comma b dy, as opposed to the deltas. All right, that's for our class. That's purely notational. Df, dx, and dy are literally the same thing as the delta x, delta y, and a delta f from above. It just means if I change, a small change in the x, small change in the y, or small change or a change in the f. Okay. I don't like to use this notation. I hate the word that they use, differentials, for this, because in mathematics, df is actually a mathematical concept. Dx is a mathematical concept. Dy is a mathematical concept. That doesn't just mean something as simple as change. And so when calculus books kind of use this notation, when there's a perfectly good notation with the deltas, right, that make perfect sense as well, I always find it kind of silly. Because again, these things actually mean, the dx's, df's, and dy's actually mean something very serious in math. And it's really bad to see the notation kind of abused in a way. Okay, so I'm gonna keep with the deltas, but just note that you'll usually see this in terms of dx, dy's, and df's. All right, let's do an example. Maybe maybe we'll talk about these dx, dy's towards the very, very end of class. Because what's going to happen is we're going to see some very big theorems at the very, very end of class. In a way, they're going to look very kind of unrelated, but they actually all come from the same fundamental principle. And that fundamental principle involves the real mathematical versions of these dx, dy's, and dz's, or whatever, if you're doing higher dimensions. So I might talk about it a little bit. All right. So let's do a simple example, and we'll end after that. So for example, let's say we're manufacturing cylindrical cans, right? Let's keep things simple. Let's just say cylindrical cans. We're not even our manufacturing plant only does the cylindrical part of the can. All right, no top, no bottom. All right, no top, no bottom. Good exercise, maybe just for yourself. Figure out the same exact problem if you did have a top or a bottom. Computations will just change a little bit, very slightly. But I just want to keep things very, very simple. Okay, so we manufacture essentially cylinders, all right? Let's say this cylinder, what's going to be a can, the radius should be 2 inches, all right? And let's say the height, I should write this out, radius R, and let's say the height h should be 5 inches. All right. Okay. If we are going to manufacture this, how much material does it take to manufacture one can? Well, that's going to depend on the area, the surface area of this cylinder. And the surface area of a cylinder is going to be it's going to be a function of the radius and the height, right? If your radius gets bigger, obviously you're going to need more material. If the height gets taller, you're going to need more material. So that's going to be pi r squared h. And if you want to do the top and the bottoms of the can, right, you just add the appropriate areas of the discs on top and the bottom. Okay, so that's going to be my area. So the thing is, well, in my manufacturing process, perhaps my machines aren't completely precise, right? There could be errors. Maybe it'll make the radius a little too small. Maybe it'll make the height a little too big, right? So I want to know, if I make, a small error in terms of the radius, how is that going to affect the total surface area of the can, right? Which of course is going to affect the manufacturing cost, right? If I make the height maybe a little too small or a little too tall, how is that going to affect the surface area of the can, right? And again, that affects how much it costs to manufacture this can. Okay. All right. So essentially, I'm asking, what is delta A, right? If I make a small change in the R or the H, or both together, right, how much is the surface area of my can going to change? Okay. All right. Well, calculating it for real, right, is perhaps going to be difficult because, we've got a square and all that, right? So let's try to do something super, super simple that a first grader could do. Delta A is going to be A sub R. And we're interested in making cans, right, that are 2 inches in radius and 5 inches in height. So we want to look at A sub R at 2, 5, right? Because we're thinking about deviations away from the can that we actually want, right? So that's why 2, 5 is our base point. Okay, delta R, and then plus A sub H, 2, 5, delta H. All right. So once I've calculated this, right, this guy's going to be a number, this guy's going to be a number, everything is going to be super, super, super simple. Okay, so A sub R, 2, 5, well, there's my formula for A. A sub R is going to be 2 pi RH. And so A sub R at 2, 5 is going to be 2 times pi times 2 times 5, 20 pi. Okay. A sub H is going to be 2 pi R. And so A sub H at 2, 5 is just going to be 2 times pi times 2, which is going to be 4 pi. Okay. So my change, delta A, is going to be approximately 20 pi delta R plus 4 pi delta H. Okay, so this tells me, again, if I have some manufacturing error, right? If my radius is made too big by a certain amount, 0.1, let's say, and let's say my height is made too small by a certain amount, let's say minus 0.2, then I know the area of my can is going to be, the deviation from what I actually want is going to be roughly 20 pi times 0.1 plus 4 pi times minus 0.2. All right, so I guess 2 pi minus 8/10 pi, 4/5 pi. Let me write it like that. So 6/5 pi. Okay. And so one conclusion here is if the radius changes by just 0.1, right? Even if the height goes down by changes by 0.2, right? My surface area is actually increased by 6/5 pi. All right. Okay, so that again gives me a very, very rough estimate for the change in whatever function. All right, so that's pretty much it for this section. Again, this is a very, very light section, which is fantastic because you really should be spending quite a lot of time on the next two sections, which is optimization, Lagrange multipliers, and which will be the next lecture. Oh, I guess I should say one thing. If you do have a 3-variable function, everything applies exactly the same, right? So a 3-variable function is going to be approximately, and you can guess by now, it's going to be df dx, x minus a, plus df dy, y minus b, plus df dz, let's say z minus c, right? And this is if you're approximating at the base point of a comma b comma c, at a comma b comma c, a comma b comma c. And again, you would know if you were doing this in an application, you would need to know that number, but it would just be a number, that number, and that number, right? Maybe 3, 4, and 5. A is also known, right? Sorry, I forgot my last term. Plus f of a comma b comma c, right? And again, you would also need to know this guy. So everything about the base point, and then you can estimate values of your function anywhere you like just by knowing how to add and multiply. Okay. All right, if you want to extend it to 4 variables, 5 variables, whatever, it's pretty clear how you would do that. But we'll just keep with 2 or 3 variables in our class. Okay, so hopefully this is pretty straightforward. Again, the last section for this week is very straightforward because we're doing the easy stuff. Last section is going to be integration. We're doing the easy stuff for integration, the easy basics, and then we'll get into the really serious stuff next week.